Somewhere above your head right now, farther away than any human voice has ever reached, a machine older than the internet is still talking to us. It has no crew, it has no screen, it runs on less electricity than the small bulb inside your refrigerator, and yet this tiny, ancient piece of hardware is quietly rewriting what scientists thought they understood about the space between the stars. It was never built to last this long, never expected to still be working, and certainly never expected to be the single most important source of new physics on the planet in the year 2026. Engineers who have spent decades reading its signals are no longer using calm, careful words like unexpected or notable. They are using words like impossible, baffling, and we got this wrong. This is the story of Voyager-1, the oldest working spacecraft humanity has ever built, and the strange, unsettling discovery it just handed back to Earth. Here is what almost nobody talks about. It is not only what Voyager-1 found out there that should hold your attention, it is what that discovery means for the safety of everything living on this planet right now. It is what is quietly happening to the spacecraft itself in 2026, a story most people have never heard. And it is a specific date, already locked into the calendar, only a few months away, that will mark a moment our species has never reached before in the entire span of human history. Stay with me, because by the time this is over, the night sky is not going to look the same to you ever again. I am your host, and this is your channel. Subscribe now if stories like this pull you in, because we are only getting started. Let's go back to where it all began. On a September morning in 1977, a rocket lifted off the coast of Florida, carrying a spacecraft with a job that sounded almost boring on paper. Fly past Jupiter, fly past Saturn, take some photographs, gather some readings, then fade quietly into the dark and go silent forever. NASA gave the mission 4 years, maybe 5, and quietly expected to close the file on it sometime around 1981 or 1982. Nobody involved thought they were launching a machine that would outlive most of their own careers, let alone become the single most far-reaching object our species has ever built with its own hands. Voyager-1 did not fade away. It swept past Jupiter in March of 1979 and beamed back the first close, detailed portraits of that giant planet human eyes had ever seen. Images of storms larger than entire worlds and moons nobody had properly studied before. It swung by Saturn in November of 1980, capturing the rings in a level of detail that reshaped textbooks, using each planet's gravity like a slingshot to pick up more speed and more distance with every pass. By the end of the 1980s, Voyager-1 had already traveled farther from Earth than anything ever built by human hands, and it was still transmitting, still functioning, on electronics that today's engineers look at and shake their heads over, hardware built before most of the scientists currently studying its data were even born. Then, in 2012, 35 years after launch, Voyager-1 did something no object from Earth had ever done. It crossed the heliopause, the outer edge of an invisible bubble blown outward by our own sun, and stepped into the actual space between the stars. Here is how to picture it. The sun does not just give us light and warmth, it constantly releases a stream of charged particles called the solar wind, which blows outward in every direction, pushing against the darkness beyond, and forming a giant protective bubble wrapped around our entire solar system. Every planet, every moon, every asteroid, every spacecraft we have ever launched, and every living thing that has ever existed sits inside that bubble. The outer edge, where the solar wind finally runs out of strength and the pressure of interstellar space pushes back from the other side, is called the heliopause, the true physical border of our solar system. Everything inside it is ours. Everything outside it belongs to something else entirely. In 2012, Voyager-1 crossed through that edge and came out the other side, becoming the first physical object our civilization has ever sent into true interstellar space. And then, remarkably, it kept transmitting. Right now, at this very moment, we have a working scientific instrument sitting in interstellar space, a region no telescope, no satellite, and no theoretical model built from the ground had ever measured directly from within. and what it began reporting back did not match a single prediction anyone had made. For decades before Voyager-1 got there, physicists had built detailed, peer-reviewed, carefully tested mathematical models describing what interstellar space should look like. These were not guesses. They were the work of some of the most respected scientists alive, and nearly all of them told the same basic story. Calm, thin, and quiet. A cosmic hallway between star systems where particles drift slowly and almost nothing happens. Voyager-1 walked into that supposedly quiet hallway and found a storm instead. Starting in 2017, its plasma wave instrument began detecting something nobody had planned for and nobody could immediately explain. A low, steady, persistent hum buried in the interstellar plasma that, according to every existing model, simply should not have been there in the way it was. This was not a one-time blip or a sensor glitch. It was a continuous signal, showing up year after year, detected across a stretch of space over 900 million miles wide. To put that number in perspective, the distance between the Earth and the Sun is about 93 million miles. This single signal has been tracked across a region roughly 10 times that length. When researchers studying this data published their findings in the peer-reviewed journal Nature Astronomy, their conclusion was blunt and unambiguous. Interstellar space is not the smooth, uniform, empty void that the old models described. It is turbulent, with structure at every scale, from distances you could measure with a tape measure all the way up to distances spanning millions of miles. A hidden complexity that had been completely invisible to us simply because no instrument had ever been sitting inside it before to check. Every model built to describe the universe beyond our solar system had been built from the outside looking in, from a planet, using telescopes, mathematics, and theory alone. Now, the first instrument we have ever physically placed inside interstellar space is telling us those models were missing something fundamental, that the region just beyond our home is more complex, more dynamic, and more structured than anyone had assumed. Here is where this stops being abstract and becomes personal. That discovery does not stay out there. The same bubble that separates us from this turbulent region is the exact bubble that shields life on Earth. The heliopause is not just a line on a diagram, it is a shield, deflecting the most dangerous cosmic radiation from distant exploded stars before it reaches the inner solar system at full strength. If that shield is less stable or more variable than our models assumed, the implications for biology here on Earth could be significant over long timescales. We do not yet know the answer, but the fact that scientists now have to ask the question marks a real shift in how we understand our own vulnerability as a species. Now the story takes a turn nobody saw coming. In 2023, Voyager-1 nearly died for good. For 5 straight months, the spacecraft kept transmitting a signal back to Earth, but what it sent was gibberish, scrambled, corrupted code that engineers at NASA's Jet Propulsion Laboratory, after decades of experience reading everything this spacecraft had ever sent, simply could not decode. The instrument was alive, the signal was arriving, but whatever it was trying to say had become unreadable. The cause, once tracked down, was almost unbelievable. A single memory chip in the flight data system had physically deteriorated after nearly 5 decades of constant exposure to cosmic radiation, corrupting the exact section of software responsible for formatting and transmitting scientific data. No alarm had gone off, no warning had been sent. The chip had simply, quietly failed after 46 years of non-stop operation in the harshest environment any human-made object has ever been placed inside. In any normal engineering situation, you fix a broken part by walking over and replacing it. Here, the broken part was 15 billion miles away, unreachable by any known form of transportation, with no repair mission remotely possible in any time frame that mattered. Even a radio signal took 22 hours to reach the spacecraft one way, meaning every diagnostic step, every attempt to test a theory, required a minimum 44-hour wait for a single round of communication. Engineers would study the data, form a theory, write careful instructions to test it, transmit them, wait almost a full day, receive whatever came back, analyze it, discover something slightly different than expected, and repeat, patiently, for months, all while knowing that one wrong command sent across that distance could permanently end the mission with 0 chance of recovery. The team at JPL succeeded. They realized the corrupted code could not be repaired in place, but it could be relocated, carefully split into smaller sections and stored in different areas of the spacecraft's remaining memory, each piece rewritten to function from its new location, then reconnected as a whole. It was, in effect, remote brain surgery performed through a 44-hour delay on a machine nearly 50 years old. By mid-2024, Voyager-1 came back online, transmitting clean data again, and immediately resumed sending back more evidence of that same unexplained plasma turbulence. But none of that prepared anyone for what the data revealed about the moment Voyager-1 first crossed the heliopause back in 2012. For decades, models predicted a gentle transition, solar wind slowly thinning while the interstellar medium slowly became detectable, like a river easing into the sea. That is not what Voyager-1 found. At the heliopause, particles were slamming into each other at speeds approaching a meaningful fraction of the speed of light, generating temperatures near 30,000 degrees Celsius, not inside a star, but at the outer edge of our own solar system. Some researchers have described it quite literally as a wall of fire, a real physical concentration of extremely energetic particles forming a barrier at the edge of everything we call home. Then came the magnetic surprise, arguably the strangest twist in the entire discovery. For years, one foundational assumption about the heliopause was that the magnetic environment would change dramatically once you crossed it. The sun's magnetic field on one side, the galaxy's completely separate magnetic field on the other, two distinct systems cleanly divided at the boundary. Voyager-1 found the opposite. The fields on both sides were connected in ways no existing theory had predicted, interacting through a process called magnetic reconnection, where field lines from different sources rearrange themselves and release energy. Our solar system, it turns out, is not magnetically isolated from the rest of the galaxy at all. It is linked to it, actively exchanging energy across the very boundary that was supposed to separate everything we know from everything we have not yet explored. This is not a small correction to an existing theory. If that relationship is more dynamic and energetic than the models described, our entire understanding of how the heliosphere has protected Earth over geological timescales needs to be reconsidered from the ground up. Now, let's talk about what is happening right now, in 2026, because this story may be entering its final chapter. Earlier this year, NASA switched off Voyager-1's low-energy charged particle experiment, an instrument that had been collecting data almost without interruption since 1977. Not because it broke, it was shut off because the spacecraft is running out of power. Voyager-1 gets its electricity from three devices called radioisotope thermoelectric generators, essentially sealed containers of plutonium-238 that produce heat as the plutonium slowly decays, heat that gets converted into usable electricity. At launch, these generators produced around 470 watts of power. Today, nearly 49 years later, they produce roughly 250 watts, losing about 4 watts every single year. At some point in the early 2030s, the output will fall below the minimum threshold needed to run any instrument at all, and Voyager-1 will go permanently silent. The team managing the spacecraft has known this was coming for years, and long ago they carefully mapped out exactly which instruments to shut off, and in what order, to squeeze the maximum possible scientific value out of a dwindling power supply for as long as humanly possible. Of the 10 original scientific instrument packages Voyager-1 launched with, 7 have already been switched off. Every single one of those decisions is one of the hardest calls a scientific team can make, because each instrument lost represents a set of questions that will never be answered, and there is no way to turn an instrument back on once you decide you switched it off too soon. But here is a twist most headlines missed. Engineers have not given up. They are testing an experimental power restructuring procedure designed to reroute electricity across the spacecraft's remaining systems and squeeze extra capacity out of components running below full efficiency. Because the risk on a nearly 50-year-old spacecraft with no manual override is real, they tested it first on Voyager-2, which carries slightly more spare power and sits closer to Earth. Those tests ran in May and June of this year. If they proved safe, the same approach may be attempted on Voyager-1 itself, as soon as this July, with a real chance of switching that shut-down instrument back on. Nobody is promising anything, but with this spacecraft, betting against it has never once paid off. And now comes the date already locked into the calendar, one no human civilization has ever reached before. On November 18th, 2026, at 16 minutes and 12 seconds past 2 in the morning Pacific Standard Time, Voyager-1 will reach a distance of exactly 1 light day from Earth, so far that a signal traveling at the speed of light will take a full 24 hours just to arrive. Send a command on Monday, and you will not know if it landed until Tuesday, and you will not hear back until Wednesday. No human-made object has ever stood that far from home, and Voyager-1 will cross that threshold while still alive, still transmitting, and then it will simply keep going. Every hour, it travels roughly another 38,000 miles deeper into interstellar space. At some point in the 2030s, the last signal will arrive, and there will be nothing after it. But even then, Voyager-1 does not actually stop. There is nothing out there to slow it down. No friction, no atmosphere, no meaningful gravity. It will simply keep moving silently at 38,000 miles per hour into darkness with no end on any human timescale, carrying the golden record bolted to its frame, continuing a journey that began on an ordinary morning in September 1977, when a group of engineers pointed a machine at the stars and expected it to last only 5 years. That record deserves a moment of its own, because it is one of the strangest and most beautiful objects our species has ever created. It is a gold-plated copper disc mounted to the outside of the spacecraft, carrying greetings recorded in 55 different human languages, the sound of rain falling across a forest, the sound of ocean waves, the sound of human laughter, 90 minutes of music selected from cultures spanning the entire history of human civilization, and a map built from the positions of pulsars, designed to show whoever eventually finds it exactly where in the galaxy our small planet sits. Carl Sagan, who helped design the record, once described it as a message in a bottle cast into the cosmic ocean, and that is exactly what it is. Whoever eventually finds it, whether another civilization millions of years from now or some form of intelligence we cannot yet imagine, it will tell them something simple and true: that there was a species here, that they were curious, that they reached outward, that they built a machine out of metal and electricity and mathematics and launched it beyond everything they had ever known, carrying the sound of their own laughter with it. It will still be drifting long after the sun swells into a red giant and swallows Earth's orbit, long after every human city, every archive, and every stone we ever carved our names into has turned back into dust. And right now, it is riding on a spacecraft that runs on less power than the bulb above your bathroom sink. The persistent plasma emission detected since 2017 is not just a strange anomaly. According to researchers studying it, it may be the very first continuous, real-time measurement of interstellar plasma density our species has ever obtained. Before this emission was detected, scientists could only take isolated snapshots of plasma density out there, triggered by specific events like the shock waves produced when massive eruptions from the sun eventually rippled all the way out to the heliopause, valuable but scattered, like trying to understand the weather across a continent by checking one thermometer once a year in one city. This emission offers something much closer to a continuous feed instead, a running portrait of interstellar plasma as the spacecraft physically moves through it, day after day, year after year, showing that interstellar space has texture, weather, and structures built from charged particles and magnetic fields stretching for millions of miles, interacting with the outer boundary of our solar system in ways no Earth-built model could ever detect or predict. There is still a genuine, unresolved question sitting at the center of it all, one the scientific community has not yet been able to answer. The emission could come from ordinary thermally excited plasma oscillations, the natural vibration of plasma particles interacting with their surroundings, a real discovery, but one that fits comfortably inside existing physics without requiring anything to be rebuilt. Or it could be something called quasi-thermal noise, a different physical mechanism carrying information about plasma density and temperature in a subtly but importantly different way, one that would force scientists to substantially rewrite their models of the interstellar medium. Nobody currently knows which. Telling the two apart would require either more data from a spacecraft producing less of it every year, or an entirely new mission built specifically for this purpose, and none currently exists or is funded. Even if one launched today, it would not reach the heliopause for at least 25 years, meaning that when Voyager-1 finally falls silent, this question closes with it, unanswered, for at least a generation. Sit with that fact for a second, because it is easy to lose it in the middle of all the physics and the engineering. Right now, in 2026, the only living scientific instrument humanity has ever placed in interstellar space is 49 years old. It was built using technology that predates personal computers. It runs on less electricity than the small light above your kitchen stove, and it is sending back information that is actively changing how we understand the universe and our place inside it. We have built things far larger since then, far more powerful, far more expensive, and far more technologically advanced. None of those things have told us what Voyager-1 is telling us right now, because none of them had the one quality that actually mattered here: the audacity to simply keep going long enough to actually get there. There are questions about the universe that can only be answered from inside it, not from a telescope on a hilltop or a satellite orbiting Earth, only from a machine that physically crossed the boundary and kept talking. We have exactly one such machine, old, fading, running on 4 watts. As long as it keeps whispering back across 15 billion miles and 22 hours of delay, we owe it our attention, because when it finally stops, some of the biggest questions we have ever asked go quiet along with it. One machine, 4 watts, one chance to listen. The real question is whether anyone is paying attention while there is still time. If this kind of story is what you come here for, hit subscribe and turn on notifications, because we are going even deeper into the edges of what science actually knows next time. Drop a comment below with whatever surprised you most, and while you're there, let us know which part of the world you are watching this from. We genuinely love seeing how far this channel reaches. And if you know someone who would find this as fascinating as you just did, send this their way. Thanks for watching, and we will see you in the next one.